Bismillahirrahmanirrahim. Welcome to lecture number 23. The topic is theory of automata, and we are discussing conversion between FA, transition graph, and regular expression. This is the outline of the lecture. We will continue the previous topics. It's actually the same topic. We are talking about Klein's theorem. So we will revise what we have covered in previous lecture. So we make a background to continue our discussion in the next topics in Klein's theorem. In last lecture, I gave you a homework. It was build an FA corresponding to the union of these two FAs, that is FA1 union FA2, where FA1 is given below, FA2 is given below. If you look to FA1, so FA1 accepts even numbers of A's and B. And if we look to FA2, it accepts odd number of A's or B. And as a homework, we have to combine these two FA in the union. So regular expression of FA1 may be A plus B into A plus B whole star. That is language L defined over sigma AB, having words of length even. And regular expression for FA2 may be R2 is equal to A plus B into A plus B whole star, and language L defined over sigma AB, having words of length odd. Now, to build a new FA, we use the same technique we discussed in last lecture. We create a new state. Let's call it Z1, and we take it as initial because it contains x1, y1. And since x1 is final as well, so therefore this is both initial and final. So in x1 reading A, we go to x2. In y1 reading A, we go to y2. This is called Z2. x1 reading B, we go to x2. y1 reading B, we go to y2, which is the same as the previous state. So we make a new Z2. Z2 is equal to x2 y2, and since y2 is final, we make it final. Now x2 reading A, we go to x1. y2 reading A, we go to y1. x2 reading B, we go to x1, and y2 reading B, we go to y1, and it's the same as z1. So basically, when we create an FA based on this transition table, we get this one: z1 plus minus and z2 plus and AB and AB. So basically it's the union of these two FA, and it accepts both even number of A's and B's and odd number of A's and B. Now the next rule is rule number 4, that's the concatenation of two FAs. It means using the FAs corresponding to R1 and R2, and FA can be built corresponding to R1 concatenated with R2. Let's say we have two FAs. R1 is A plus B whole star into B, that is language L of strings ending at letter B, and R2 is A plus B whole star into AA into A plus B star, that is the language L of strings containing double A. To build a new FA, we make this transition table. We make Z1, which is the initial state of FA1. Now reading A, we go to X1, which is same as Z1. But reading B, we go to the combination of these two, X2, Y1, which is Z2. So Z2 is a new state. It is X2, Y1. So X2 reading A, we go to X1. Y1 reading A, we go to Y2. This is Z3. Now X2 reading B, we go to X2. Y1 reading B, we go to Y1, which is basically this Z2. Now we have a new state Z3. We take it. It consists of X1, Y2. X1 reading A, we go to X1. Y2 reading A, we go to Y3. It's a new state, so we name it Z4. X1 reading B, we go to X2. Y2 reading B, we go to X2, Y1, which is Z2. Now this Z4 is a new one, so we take it. It is X1, Y3. X1 reading A, we go to X1, and Y3 reading A, we go to Y3. This is Z4. Now X1 reading B, we go to X2, Y1, and Y3 reading B, we go to Y3, which is a new state, so we name it as Z5. Now in Z5, it says X2, Y1, Y3. At X2 reading A, we go to X1. At Y1 reading A, we go to Y2. At Y3 reading A, we go to Y3. It's a new state, so we name it as Z6. X2 reading B, we go to X2, Y1. Y1 reading B, again we go to X2, Y1. Y3 reading B, we go to Y3. It's the same as the previous state Z5, so we do not create a new state. Now there is Z6, which contains X1, Y2, Y3. X1 reading A, we go to X1. Y2 reading A, we go to Y3. And Y3 reading A, we end up at Y3. So it's the same as Z4. Now X1 reading B, we go to X2. Y2 reading B, we go to x2 y1, and y3 reading b, we go to y3 is the same as the previous state, z5. No more new states are created, so we stop here. And if we build the resultant FA, it looks something like this, which is basically FA, or finite automata, for the concatenation of these two strings. It was the quiz that I gave you in last lecture. It was about R1 for FA1. It accepts language L of strings having even length, and this is a second regular expression for FA2, which accepts words of length odd. So basically we solved this problem in the previous slide, I think. This one. But here we were looking for the union of these two FAs. In the quiz, you were asked to find the concatenation of two regular expressions. So it's the same FA as given here, and you have to build FA, that is the concatenation of these two. So basically these two will be taken as a single state. So Z1, initial state, we do not consider it as a final state anymore. So X1 and Y1, initial state of both states. Now reading A, we go to X2 Y1, X2, and reading Y1, reading A, we go to Y2. So this is named as Z2. Now X1 reading B, we go to X2, and Y1 reading B, we go to Y2, which is Z2. Now Z2 is X2 Y2, and X2 reading A, we go to X1, and Y2 reading A, we go to Y1, which is Z1. Now X2 reading B, we go to X1, and Y2 reading B, we go to Y1, which is Z1. And its corresponding FA can be built like this. So this is basically the FA that accept these strings. So even followed by odd, which are basically odd numbers. So basically if you look to this FA, so this FA accepts strings of length odd. Rule number 5. Building an FA corresponding to regular expression R star using the FA corresponding to R. If a given FA already accepts the language expressed by the closure of certain regular expression, then the given FA is the required FA. However, the method in other cases can be developed considering the following examples. Let's say this is a regular expression, and you see it does not contain a statement like this. Right? So we can build regular expression for this star by this. So we take 1 time and 2 times, and we will be combining these two. Now the corresponding FA is something like this. We take the initial state Z1, which is Y1. The initial state is also final because you see this will accept lambda. So that's why it's final. Now Y1 reading A, we go to Y2, which is Z3. And Y1 reading B, we go to Y1. This is Y1 reading B, we go to Y1. And we treat it as a non-final because in order to accept lambda we make it final, but in order to accept other instances we make it non-final. So Z2 is Y1, then Y1 reading B, we go to Y2, Y1 reading A, we go to Y2, and Y1 reading B, we go to Z2. This is new one, Z3, Y2. So Y2 reading A, we go to Y3, and Y2 reading B, we go to Y1, which is Z4. Then Y2 reading B, we go to Y1. Y2 reading B, we go to Y1. Now Y3, Y1. So Y3 reading A, we go to Y3, Y1. And Y1 reading A, we go to Y2. A new state. Y3 reading B, we go to Y3, Y1. And Y1 reading B, we go to Y3, Y1, which is Z4. Now Y3, Y1, Y1, Y2. Now Y3 reading A, we go to Y3, Y1. Y1 reading A, we go to Y1. Y2 reading A, we go to Y3. Yes, Y3. So this is Z5. Now Y3 reading B, we go to Y3, Y1. Y1 reading B, we go to Y3, Y1. And Y2 reading B, we go to Y3, Y1. So this is same as Z4. So its corresponding FA can be built like this. To accept lambda, we have this state, and to accept other combination, like all possible combination having double A. So this is single A, single double A. These are other double A's are basically, it's actually consisting of double A. So actually double A can be accepted. I mean, once double A occurs, there can be any possible combination of AB. Actually this FA can be reduced further. How it can be reduced? It can be reduced like this. These two final states can be combined. It can be made as a single state with a loop of AB. This is A. Yeah, I think this is not needed, so this can be removed. So this is the FA for R star. Let's take another example. Let's take FA that accepts odd number of B's and any number of A's. So you see B occurs in odd clumps. This is the corresponding FA. We can build this FA by making two FAs. This FA as a duplicate, and we take Z1 as X1 initial and final. X1 reading A, we go to X1. X1 reading B, we go to X2 X1, which is Z3. Now Z2 X1. X1 reading A, we go to X1. X2 X1 reading B, we go to X2 X1, which is same as Z3. Now take X2 X1. X2 reading A, we go to X2 X1, and X1 reading A, we go to X1, which is same as Z3. X2 reading B, we go to X2, and X1 reading B, X1 reading B, we go to X2 X1. So this is Z3. Now if we build its corresponding FA, it will look something like this, and this is basically the corresponding regular expression. This will make sure that lambda can be accepted, and it accepts B's in odd clumps. So you see single B is accepted here, and one single odd number of B's happen, then any combination can be accepted. So this is its corresponding FA. Here is a quiz to practice on this closure property. Build an FA corresponding to the closure of the following FA. This FA, its regular expression is not written. You think about what can be the regular expression for this language. And this is solution, but I will discuss this solution in next lecture. So this is basically the end of Kleen's theorem. So let's summarize Kleen's theorem. Kleen's theorem part 1 states that if a language can be accepted by an FA, then it can be accepted by TG as well. We prove this. Then we discuss if a language can be accepted by TG, then it can be expressed by a regular expression as well. Then we discuss if a language can be expressed by a regular expression, then it can be accepted by an FA as well. So basically these three parts we discuss, and we prove this statement by using different examples. Okay, so this is non-deterministic finite automata. So far we discussed FA and TG, but non-deterministic finite automaton is another type of machine which lies somewhere in the middle between FA and transition graph. So an FA is a transition graph with a unique start state and have single letter as label of transitions. In transition graph, we have discussed that there can be multiple start states and there can be substrings as labels of transitions. But NFA is different. So the definition of NFA is given. NFA is collection of three things: finite set of states having exactly one initial and some, maybe none, final states. Finite set of input letters, finite set of transitions showing where to move if a letter is input at certain state. Remember that lambda is not a valid transition. There may be more than one transition for certain letters, and there may not be any transition for certain letter. And as in the case of TG, is a relaxation. Let's take an example of NFA. This is initial state, one final state, two final state, and it accepts A and A, B. So you see for A, there are three transitions. At this state, there is no transition for A, there is no transition for B. Similarly here, similarly here. So this NFA accept language consisting of A and AB. An NFA can be considered to be an intermediate structure between FA and transition graph. This is what we discussed already. Let's take another example. This is an NFA. Here for A, we have multiple transitions, and this NFA accepts language of strings containing double A. This is the corresponding regular expression. You see at this state there is no transition for B. It's okay, in NFA it is acceptable. By Klee's theorem, if a language can be accepted by an FA, then there exists a transition graph accepting that language. This is what we discuss in Klee's theorem. Since an NFA is a TG as well, therefore there exists an NFA accepting the language accepted by the given FA. So FA and NFA are equivalent to each others. By equivalent means, if a language can be accepted by FA, then there exists an NFA that accepts the same language. Let's take another example. FA corresponding to this regular expression is given as, this is FA, deterministic FA. You see there is transition for A, B, and unique transition. But its corresponding NFA, its equivalent NFA can be given as AB and B. So FA is basically equivalent to NFA in terms of describing languages. Let's take another example of FA. This FA accepts language L of strings containing double A. This FA may be equivalent to this NFA. I give you a quiz. Build an NFA equivalent to this FA. So this FA, if you remember, it accepts language L of strings containing triple A and triple B. And the middle lines are just to make sure that every state has transition for A and transition for B. If you remember the regular expression for this language, it was A plus B whole static into triple A plus triple B plus triple B into A plus B whole star. So it's NFA. You need to think about how to skip these intermediate lines. I think it's very simple. Think about it and I will give you solution in next lecture. So every FA can be considered to be an NFA as well, but the converse may not be true. Remember, in NFA there are certain relaxations. So if we do not use those relaxations, we can build FA. But if you use those relaxations, then you have an NFA. So every FA is basically NFA, but the converse may not be true. Similarly, every NFA can be considered to be a transition graph. Remember, in transition graph there were certain relaxations. If you do not use those relaxations, then it can be equivalent to NFA or FA, but the converse may not be true. Thank you very much.